Hey everyone, this is Nick Jacobs, your intermediate algebra instructor here at Yavapai College. I wanted to go over a chapter 7 review, just covering some of the types of questions that you might see on your chapter 7 exam coming up. So let's get started. Kind of a different format for this. I'm going to go over, some different things that you might see on the test, and then we'll get into some example questions. So on section 7.1, that was an introduction to radical expressions. And so what we did there is we evaluated, simplified, and solved rational expressions. So let's go into some examples. This is number 3 on your chapter 7 practice exam. Again, your numbers and variables and things like that might be a little bit different, but the question should be the same here. So the question is here, find any values of the variable that make the expression undefined. So we want to know what values of the variable y make this expression undefined. And we know that our denominator cannot be 0. So our denominator cannot equal 0. So basically what we do here is we set the denominator y squared minus 1 equal to 0. And that's going to give us all the values of y that would make the denominator 0. And the denominator cannot be those values because it would make that undefined because we cannot divide by 0. So let's go ahead and do that. So y squared minus 1 equals 0. We're going to add 1 to both sides. So y squared equals 1. And then we take the square root of this. Okay, square root of 1, which is going to make this a plus or minus, right? And we know that the square root of 1 is 1. So this is going to be a -1 and 1. So any values where y is equal to -1 or 1 are going to make this denominator 0. And you can, so it's going to be a there, and it's going to be -1, 1. You can, quick verify this yourself by substituting in both of those and seeing, yeah, if I substitute -1 in here, it does give me 1. 1 minus 1 is 0. Substituting 1 in, 1 minus 1 again is 0. So both of those make the denominator equal to 0. And that means that it's undefined. So let's do another example. Number 4 here on your practice exam says to simplify the expression. So we have 20 times x times y to the third over 25x squared y squared. So one method that I used when I was simplifying these is I kind of broke these down into all multiplication and then canceled. So I can break down 20 into something like 2 times 2 times 5. That's called the product of primes. And then we have the times x times y cubed, which is y times y times y. And then on your denominator, 25 breaks down into 5 times 5. X squared is x times x. And then y squared is y times y. And so at this point, what you could do is you could cancel. So I'm going to cancel out one of these 5s on top and bottom. I'm going to cancel an x out. I'm going to cancel out 2 of the y's there. So basically, your answer is what you're left over with. So I'm left over with 2 times y on the top, and then 5 times x on the bottom. So that's going to be 4y over 5x. So that's your answer. All right, one more on section 7.1. Again, simplifying. We have to simplify. So here you can't just go ahead and start canceling z squareds and z's and the 18 and 21. You can only cancel if you have products. So if you factor these. So what I'm going to do is I'm going to factor the numerator and factor the denominator and then see if any of those factors cancel. So you see in our numerator here, this breaks down into z. Let's see, factors of 18, that give me -9. That's going to be -3 and -6. So we have z minus 3 and z minus 6. And then on the bottom, we want factors of 21 that give us a -10. So that's going to be -3 and -7. So then here, again, now that it's all factored into products, I can cancel on top and bottom. So I can cancel this z minus 3 and the z minus 3. And I'm left with z minus 6 on top over z minus 7 on the bottom. All right, section 7.2 was multiplying and dividing rational expressions. So let's get into that. Kind of a similar type of concept here as what we just did on 7.1, where we want to factor all of these expressions and then see if I can cancel any common factors. So you might recognize this z squared minus 1 and z squared minus 4 as a difference of two squares. For those of you who need a refresher, a difference of squares would be both your first and your last term are perfect squares. And we can break it down into something like that. So if I have a squared minus b squared, it's equal to a minus b times a plus b. So this z squared minus 1, yes, both of those are perfect squares. So I can take that and break it into z minus 1 times z plus 1. And then that's over, again, this is a difference of two squares. It would be z minus 2 and z plus 2. And you can FOIL these out, right, to make sure that they match these if you really need to. And then I have a z minus 2 and a z plus 1. And if it makes it easier for you, you can always put those in parentheses, okay? And then those kind of match up now with these products. So I can cancel diagonally. So the z minus 2, the z minus 2, and the z plus 1 and the z plus 1. So then I'm left over with just z minus 1 over z plus 2. And that is it. Okay, let's go to number 10 on the practice exam. So this is divide. So remember when we have division, okay, we need to do this. We need to keep, switch, and flip, okay? So we're gonna keep this first expression, x minus 3 over 2x. We're gonna switch the division to multiplication, and then we're gonna flip this second expression. So we have 6x on top over 3 minus x on the bottom. Now, we can kind of go ahead and see if I can start to cancel anything. Well, I noticed the 2x and the 6x, I can definitely simplify those. But I have the x minus 3 and the 3 minus x. Now, the trick here with this 3 minus x is going to be to factor out a -1. I'm going to rewrite this. I have x minus 3. Let's write this 2x out into 2 times x. 6x is 2 times 3 times x. And then 3 minus x, I can take out a -1. So really it's -1 times x minus 3. And if you distribute the -1 in here, you're still going to get the original 3 minus x. Okay, so I didn't change anything. I just factored out a -1. So then I can start to cancel here. We can cancel a 2, we can cancel an x, and now I can cancel these x minus 3s. So what am I left with on top here? I have a 3, and I have a -1 on the bottom, and that's just going to be -3. All right, section 7.3 was on adding and subtracting rational expressions. And most of these in 7.3, I believe, yes, they had like denominators. So we're only going to do one example here. So all the questions in 7.3 had a common denominator, and we need that when we subtract rational, excuse me, we need that when we subtract rational expressions, excuse me. So let's go ahead and do that. I noticed the t or the 9t plus 4 and the 9t plus 4 are the same. So we can go ahead and kind of combine the numerators there. Now, the only thing with this one is we have a minus, so that minus sign right here applies to both terms on the numerator there with the 5t minus 4. So let's go ahead then and distribute that minus sign. So we have 14 minus 5t plus 4 all over 9t plus 4. And that's equal to, let's see here. Whoops, I missed a t. This is 14t. So now this is 9t plus 4 on the top and a 9t plus 4 on the bottom. Interesting. Sorry, I just wrote that plus sign. It kind of looks like a t. The reason why I put that little loop in the t's is to not confuse them with plus sign. So let's not do that. Let's not put a loop in the plus sign. But here, both of these things are the same. Well, those are just going to actually both cancel out, and I'm just left with 1. Right, and sometimes people will put 0 here if they both cancel. Well, that doesn't make sense, because if I factor out a 1 from these, okay, I have really 1/1 left over, right, which is 1. So that's why that's 1 and not 0. Section 7.4, we did adding and subtracting rational expressions with unlike denominators. So when we add and subtract with unlike denominators, we need to make a common denominator. And so let's kind of model that here. So in order to do that, what we do is we find the least common denominator of your two denominators. So in this case, it's 3x and 7x. And we did that by listing out the products here. So 3x is 3 times x, 7x is 7 times x. The LCD is, that's LCD. The LCD is equal to basically the most number of these that you would have. So we have a 3, we have a 7, and we have an x. If I had something like 3x and a 7x squared, I would break that up into 3 times x and then 7 times x times x. And so my LCD, I would need 2 of the x's because it's the most number of those. Okay, but this isn't the question. So my LCD is equal to 21x in this case. And what I kind of do here is I multiply these by what term was missing. So our LCD was 3 times 7 times x. 3 times x is missing a 7. So if I have 1/3x and I'm trying to get that common denominator, I'm going to multiply top and bottom by 7. Okay, or 7/7 basically. Okay. And then I'm going to take this other one. We have 4/7x. And that one's missing a 3. So I'm going to multiply top and bottom by 3, or 3/3. So I'm not changing these at all because I'm really essentially multiplying them by 1, right? 7/7 is 1, 3/3 is 1. But that's going to allow these to have a common denominator now. So 1 times 7 is 7. 3x times 7 is 21x. That's our LCD. And then 4 times 3 is 12. And then again, I have a 21x. So now that I have a common denominator, I can take this. Oops, let me erase some of that. This pen just started to do some weird things here. I don't know why it's not erasing. That is interesting. I've never had that happen before. Oh, there we go. Okay. Sorry. So let's add the 7 and the 12. So we do 7 plus 12 over the 21x, and that's 19/21. All right, let's do another one with a non-common denominator. So this is kind of where, we have that we have to recognize that these are kind of the opposites of each other. If I just multiply, let's say this one by -1, that's going to allow the denominators to be the same. So our LCD here really is just x minus 7, but I need to be able to get that. So, one way to do that here, if I have 7 minus x, if I take this and I multiply it by a -1, then that's going to give me x minus 7. Okay, so actually these aren't equal to each other. Okay, but if I took this expression and I multiplied it by -1, then that's going to give me x minus 7. So basically you can say that this x minus 7 isn't missing anything. So I'm not going to do anything with this first expression, but the second expression, I could say, kind of like I was talking about in the last problem, what is it missing? Well, it's missing a -1 in order for those to match. Okay, so in order for this to become an x minus 7. So this is going to be 4/x minus 7. Now let's multiply this guy by -1. So this is -8 over, again, that x minus 7. And I just rearranged it, right? Because 7 times -1 when I distribute is -7. So that sign is the same. -x times -1 is a positive x. So now I have 4 plus -8 over x minus 7, and that is equal to -4 over x minus 7. And that's the answer. All right, let's do another one here. So, and they kind of give you a hint here. So simplify the expression, write your answer in lowest terms and leave it in factored form. So leave it in factored form. That's kind of the hint. So that means that maybe I'm going to factor this x squared minus 9 because I know that that's x minus 3 times x plus 3. That's a difference of squares. So this guy really isn't missing anything if you want to think about it like that. This expression 2 over x minus 3 in the denominator is missing an x plus 3. Okay, so our LCD in this case is really x minus 3 times x plus 3. So I'm going to take this guy and I'm going to say 2 over x minus 3, and it's missing that x plus 3. So I'm going to multiply this top and bottom by x plus 3. And then this other expression, again, wasn't missing anything. It's just x minus 3 times x plus 3. And so on top here, we have 2 times x plus 3 minus 1 all over x minus 3 times x plus 3. And so I'm going to distribute there. We have 2x plus 6 minus 1 over x minus 3 times x plus 3. I'm leaving it in factored form. And then we have 2x plus 5 over that x minus 3, x plus 3. So that's it. That is how we do a problem like that. Let's move on to section 7.5. This is on complex fractions. So the goals here would be to introduce them and also to simplify. So this is something like a complex fraction. Now this is kind of similar to what we did when we were multiplying, or sorry, when we were dividing these. What I like to do with these, sometimes this can confuse people, having all of these division signs. So what I do is I kind of take this bigger division line and I write it with the division symbol. So we have a fraction on top, we have a complex fraction on the bottom. I'm going to rewrite this problem. It looks like this. Okay. And now I can do that keep switch flip. So I'm going to keep this first one, change the division to multiplication, and then flip the second one. So the second one gets flipped. And now I think this looks a little bit easier. Now what I'm going to do is I'm going to write these again in a product of primes kind of. So I have a negative, we have a 2 over 21x squared. That is 3 times 7 times x times x. And then 9x to the third is 3 times 3 times x times x times x, all over 8, or 2 times 2 times 2. And now that those are kind of in a product of primes form, or just a product form, factored form, what I can do is I can cancel. So I can cancel these 2's out. I can cancel a 3. And I can cancel an x, and that's what I'm left with. So on the top there, I am just left with -3 and an x. And then on the bottom, I have a 7, a 2, and a 2, which is 28. And that's all that we can do with that one. And you can really, you know, that negative sign, that can be even with the fraction bar, or you can put it up on top. It doesn't really matter. Let's simplify this complex fraction. So this one's a little bit different. That last one was a little bit easier. So here we have an addition, and that kind of changes things a little bit. So you have a couple of different options that we've learned. We learned one method where we kind of wrote these as just a single expression, and then did the last method that we did in number 20, or question 20, or we did method 2, which was multiplying each term by the LCD. I'm going to do method 2 first, and then I'll show you method 1. So method 2 was finding an LCD of all these. So we have an x over 1, basically. Okay, x is x over 1. So we have a 1, we have an x and the x. What is the LCD of that? Well, that would just be x. Okay, So what I'm going to do here is I'm going to take this guy and I'm going to multiply everything by that LCD. Actually, let me do the original problem. I'll write in blue, and then I'll write everything else kind of in red for that LCD thing. A little bit of space there. There we go. So then I'm going to multiply all of these by that LCD of x, that denominator of x. Okay, so what is this going to do? So that's going to become x times x is x squared over, we have a 3x over x plus 7x over x. So that's x squared over, well, when we have this 3x over x, we could just cancel the x's out. So this is just 3. And then 7x over x is just 7. So then we have x squared over 10. Okay. And then the other method was taking this problem and writing, let's say, this denominator as a single fraction. And that's easy to do here because these both have a denominator of x. So I'm going to keep this x in the numerator, but then 3x or 3 over x plus 7 over x is 10 over x, right? We add the numerator, 3 and 7, gives us 10, and we keep the denominator. And then now what I can do with this is I can take this and say this is x over 1 times x over 10, right? I took this guy, x over 1 divided by 10 over x, and I changed the sign of multiplication and I flipped the second one. Okay, do you see why that kind of helps to write it out like that? You know, it's going to, you know, help you to make less mistakes when you flip that second thing. So then this is again going to be x squared over 10. So either way you do it, if you use method 1 or method 2, you're still going to get the same answer, x squared over 10. All right, let's go on to section 7.6 when we did some rational equations. Okay, so a few main goals here: solve rational equations, recognize rational expressions and equations, and then find graphical and numerical solutions to them. Okay, so number 24 on the practice exam, solve and check your answer. So here again, the difference is we're not simplifying, we're solving. Why are we solving? Because we have that equal sign in there, right? Now we have an equal sign. Now we can actually find what y is equal to. And what they want you to do on these is they want your answers in integer form, and they also kind of want you to check your answer. And that's important because in the next question we do, it is possible that you could get no solution for some of these, and you have to remember when that's the case. So let's multiply. So what do we do here? We learned that when we have these expressions like this, we can cross multiply. So I don't need to find a common denominator, whatever. Okay, I can just go ahead and I can multiply diagonally. So multiply these guys and multiply these guys. So I can take this and I can go y times 2y plus 7 equals -1 times 3. And that's going to give me, when I distribute, 2y squared plus 7y equal to -3. Now what I'm going to do is I'm going to move that -3 over by adding it, and this is equal to 0. Now what I can do is I can check, is this factorable? Okay, if it's not factorable, we would have to go to kind of back to either the quadratic formula like we did in the previous chapter, or we would have to complete the square. But I think this is factorable because I know that 2 times 3 is equal to 6, and I do have factors of 6 that add to this middle term of 7, and that's 1 and 6. So at this point, if you know this is factorable, what you could do is you could guess and check. Okay, I'm not gonna tell you can't guess and check, or you can just go through the entire process like we did way back in chapter 6. So we found this 1 and the 6, and what I did back in chapter 6 is I split the middle term. So I split this into 1y plus 6y plus 3 equals 0. So I split the 7y again into that 1 and the 6. Now we group it. So we group these two things and these two things. And that gives us, when we factor out of here, I can factor out a y from this grouped pair here. So this is going to be y times 2y plus 1. Then I can take out a 3 from that second one. And that's again 2y plus 1. And then now this guy becomes y plus 3 times that common factor 2y plus 1. And now I use the zero product property. Okay, so I take both of these and I set them equal to 0 and I solve for y. So I have -3 and I subtract 1 and divide by 2. That's -1/2. Okay, so it should be -3 and -1/2. What we would do here, they want us to use a comma to separate the answers. So that's going to be -3, -1/2. Now, again, you can go ahead and you can check this, right? So if I check it, okay, let's check the -3 first. So I'm going to take that and I'm just simply going to plug it in for where I see the y value there. And I have -1 over, this is 2 times -3 is -6. -6 plus 7 is 1. So I have -1 over 1. -3 over 3, both of those are equal to -1. So that checks out. So -3 is a solution here. And then let's check the -1/2. Let me do that over here. So I'm going to check -1/2. Sorry, this is so messy. -1 over 2 times -1/2 plus 7. Does that equal, again, does this equal each other? -1/2 over 3. And this is going to give me, let's see, 2 times -1/2 is -1 plus 7, that's going to be 6. So this is -1/6. And then -1/2 divided by 3 is -1/6. So that checks out as well. So I know that y equals -1/2 is also an answer when I check it. So again, these are your answers, -3, -1/2. All right, let's go to the next one. So this one is, again, you have to check them and it's no solution. When is it no solution? Okay, it's no solution when you check it and it doesn't equal the same thing, right? On either side. Another way that it would have no solution is if your denominator was undefined. So if your denominator gave you, one of these was 0 or both. Okay. But this one is not going to be no solution. I'll just kind of throw that out there right away. But what we want to do for a problem like this, this is a little different. So before, what we did is we cross multiplied, and we could do that because we had a fraction basically over a fraction. Well, now I have a fraction and then plus another fraction. Okay, so what do I have to do? I have to get rid of the fractions. I have to get rid of that denominator. And I could have done that here. I just think my method was a little bit easier. Okay, so this method you could have used in the last problem, but basically what you want to do is you want to get an LCD. So our LCD here is what? Well, it's just 2z because I have a 2 times a z, I have a z, and then this is 1 over 1. And the LCD of all those is just 2z. So what I'm going to do here is I'm going to take that LCD, I'm going to leave myself a little space. I'm going to take the 2z and I'm going to multiply it by all of these. Okay, so I'm going to multiply 7 over 2z times 2z, 5 over z times 2z, and then 1 times 2z. Okay, and then now I can go ahead and I can multiply those. So what happens here? Well, when I do that, okay, we notice that some cancellation occurs. So I can cancel this out. So this is just a 7. I can cancel a z here. This is a 10. And then this is 1 times 2z is just 2z. So really I have 17 equals 2z. When I divide both sides by 2, I have 17 over 2. And that's your final answer. Okay. Another thing people like to do with this, you might do something like this. You might take this and multiply the whole thing by 2z, kind of like we did, and then distribute on the top, keep your denominators, and then cancel later. So I could distribute the 2z into 7, that gives me 14z. 2z into the 5 gives me a 10z. That's over z. And then 2z into 1 gives me a 2z. And then now we cancel. So this is still going to be a 7. This is still going to be a 10. This is still going to be a 2z. And look at that. We're right back to this step right here. So either way that you want to do it is perfectly fine. But again, you do have to check to see, does this 17 over 2 make your denominator 0? Well, in this case, it's not. But let's just quick check to see if 17 over 2 is correct. So 7 over 2 times 17 over 2 plus 5 over 17 over 2. Does that equal 1? So we have 7 over 2 times 7 over 17 over 2 is 17. And then this guy is actually going to be 5. Let's see, not 5. 5 times 2 over 17. Let's see here. That's 10 over 17. Okay. So this guy actually simplifies to 10 over 17. And 7 over 17 plus 10 over 17 is 17 over 17. And that is equal to 1. So that checks out. So 17 over 2 is the answer. And it's not going to make this denominator 0. So there is a solution there, 17 over 2. All right, let's do another one, last one in 7.6, and then we'll get into the variation problems from 7.7. So this one, you kind of have a couple of different options, okay? There's that LCD method, okay? And I'm not going to show you all of that. But again, what's the LCD in this case? Well, the LCD here would be that 6x and the 5x plus the 6. So I could take this and I could multiply all of these terms, okay, by that LCD. Okay, but there is a shortcut. And I'll show you that in a second. So I could do that. I could multiply everything by the LCD. Okay, and then keep going. I can cancel that out. Let me just finish this, I guess. So I cancel those out, cancel those out. 0 times all this is just 0. So over here, I just have 1 times 5x plus 6 is 5x plus 6, minus 1 times 6x is minus 6x. Combining like terms on this side, I have a negative 1x plus 6. I subtract the 6 over to give me negative 6, and then divide by negative 1. So x should be equal to 6. And that's not going to make your denominator 0, but I will check that in a second. Okay, the other method to solving this problem is to add this to the other side. And why can I do that? Because this is a 0. Okay, if I add this to 0, it's going to give me just the positive form of this thing. So it's going to be 1 over 6. I add this expression, so that's positive 1 over 5x plus 6. Now I can do that whole cross multiplication thing. So I can take this, multiply these, multiply these. So really I have 5x plus 6 equal to 6x. Subtract the 5x on both sides. 6x minus the 5x is x. And look at that. I have the x equals 6. So that's really kind of the faster, quicker way, I would say, of doing that one versus all of this LCD method here. Okay, and now what you need to do is you do need to check it. Okay, and this is not going to give you a no solution, but it's good to just check it anyway. So I plug 6 in for x. And again, does that equal 0? So 1 over 6 times 6 is 36. And then this also gives you 1 over 36. So 0 equals 0. So that checks. So x is equal to 6. That is the answer. All right, let me get some water. Let's go on to section 7.7, proportions and variation. So a few different goals here. We're going to solve proportions, solve direct variation and inverse problems, and then solve some application problems. Now we might not do all of that. I'm going to try to focus more on the variation here. but you did have those other topics, just so you know. Actually, we will do an application problem. So question 29 on the practice exam said, suppose that y is inversely proportional to x and that y equals 8 when x equals 4. Complete parts A and B. Now I did forget to put a part B in here. Part B, we're going to say that this is find y when x equals 16. So we'll work on that later. Let's first find the constant of proportionality. So kind of as a review, this one was inversely proportional, okay? And if we remember, when it's inversely, when it says inversely proportional, it's an inverse. So that's y equals k over x. We learned that in section 7.7. And the other one is when it is directly proportional, would be y equals k times x, okay? So in part A here, when we're finding this constant of proportionality k, I'm just going to plug it in. It's inversely proportional. So I'm using y equals k over x. That's what I'm using as my base kind of function there, or formula, if you will. And then I just substitute those values that they give you to find k. So y equals 8 and x equals 4. Now I need to solve for k. So what I'm going to do is I'm going to times both sides by 4. Those cancel, so it's going to be 32. So your answer for part A is going to be 32. Now I need to find y when x equals 16. So for part B, I'm going to go back to the same formula or function, y equals k over x, and I'm going to substitute. But now I know k and I'm trying to find y. So I know that k now is 32, and I gave you that x is equal to 16, and 32 divided by 16 is 2. So y is equal to 2 in our second part of that problem. And then I think, let's see, I think I have actually 3 more questions. So I go over some table examples here. So we have to determine based on this table whether the data represent direct variation, inverse variation, or neither. And I told you that if it's direct, so if we take if all of our y divided by x's in the table equal the same number, what does that tell us? Okay, I'll have a little arrow. That tells us that that would be a direct variation problem. Okay, if all of x times y equal the same number, that would tell us that it is an inverse variation problem. Okay, and if neither of these were true, then it would be neither. It would be neither direct nor inverse variation. It might be some other type of variation that we haven't talked about yet, and that we won't talk about actually in this class, but you will maybe talk about in a different class. So let's try that. Okay, let's test here. So we're going to test whether it's direct variation. Okay, and how do I do that? I just take all of the y divided by x's and see if they equal the same number. Or if I get one that's not the same, I can just stop. So let's take 12 divided by 2. Okay, so y divided by x, 12 divided by 2 is 6. 8 divided by 3, is that 6? No, it's not. It's 2 and 2/3. So no, it's not direct variation. Not direct variation. I'll just say DV. Let's test if it's inverse. Let's test if it's inverse variation. So to test inverse, I'm going to multiply x times y. So 2 times 12 is 24. 3 times 8 is 24. I'm good so far. Let's keep going. 4 times 6 is also 24. And then I have a 12 times 2. And that is also 24. So yes, this is inverse variation, okay, with a little exclamation mark. So this is inverse variation. Now, the last part of the question we have to answer is, what is the constant of variation? Well, it's just the number that these equal. So those all equaled 24. So that means that K is equal to 24, or our constant of variation is 24. Another way to do that here is, by saying here again that, all of these X times Y's equaled 24. And that meant inverse variation. Why is the K equal to 24? Well, remember in inverse variation, our formula was Y equals K over X. Well, if I solve this for Y, I'm going to divide both sides by X. So I have 24 over X. Well, what is the K value? It's that 24. So hopefully that kind of makes sense for you. Let's do another table question. Okay. So again, the first thing that here's the table that I give you. Now on your practice exam, and maybe if you have a question like this on your exam, for some reason this table is like way off in the right corner over here. I just moved it over here for this purpose here, but just don't miss that table, okay? So same thing you have to do is determine whether the data represent direct variation, inverse variation, or neither. If the data represent direct or inverse, find an equation that models the data. Okay, so did I ask you to do that? No, I didn't ask you to do that in the last one. But then we're going to graph the equation and the data if this is one of those types of questions. So let's go ahead and do that here. So let's test. Whoops, I hate when my pen does that. If you've been watching all my videos, you know at various times it'll start kind of just drawing on its own sort of. But anyway, so here we go. Let's test for direct variation first. And to test for direct variation, again, what I do is I take all of the Y divided by X's. Okay, and so I have 11 over 2, which is about 5.5. What's 22 over 6? Is it 5.5? I don't believe so. I believe it is 3 2/3. So this is not direct variation. Let's test for inverse variation. Again, that's X times Y. So 2 times 11 is equal to 22. But 6 times 22, that is not 22. Okay, that is actually 132. So this is not inverse variation either. So this one is neither. Okay, so really part B does not apply. And then I can't, in order to graph this, all I could do is plot the points on a graph. That's all I could do. I could not, I don't have an equation for this. So I would just graph the data. But if there was an equation, so if you had a problem on your test that there was an equation, okay, well, it would be kind of something similar to the last problem. So if it was inverse variation, okay, and you needed to find that equation, okay, the equation for number 31 would have been that Y equals 24 over X. Okay, and then you would just graph that, okay, again, by plotting some of the points. Okay, so you would plot points in your graph. Okay, so hopefully that makes sense. So if it is direct or inverse, you just take what equation you would get here from that. Okay, so it is helpful to know that, yeah, your constant here in the last problem, it is 24, but why is it 24? We'll put it back into an equation. So we tested for inverse variation by multiplying X and Y's, and we got all of them equal to 24. But then if I made it into my inverse formula, which is Y equals K over X, I would divide both sides of here by X. So Y equals 24 over X. And that would have been my equation that models the data. All right. If you have questions on that, let me know. Number 33, the strength of a metal beam varies directly with its width. A beam that is 5.4 inches wide can support 2,500 pounds. how much weight can a similar beam support if it's 4.8 inches wide? So the first thing you're going to want to do here is find your constant of variation. Well, we know that this varies directly. So the formula equals y equals k times x. That's for direct variation. And we know that, and I kind of talked about this in the section 7.7 lecture, but we know that inches would be something that is independent, okay? But the pounds that the beam can support depends on how many inches wide it is, okay? So inches is always going to be an x variable. Pounds would always be a y variable, okay? And that's important when we substitute this into the problem, okay? So go back to section 7.7 lecture if you're not sure on that. But again, our x variable is going to be inches. Our y variable is the dependent variable, or it depends on x. So that's the 2,500 pounds here. So let's substitute those. So this is the given information. In order to find the constant of variation, we have to substitute both of those first to get the k value. So let's do, so we have 2,500 for y equals k times the x value of 5.4. And to solve that, all we do is divide 5.4 on either side. So we have k is equal to 462 point about 96. I'm just going to round it to the nearest hundredth. And then what I do here is I take the same equation again, y equals kx. And now I need to find how much weight, so the y value, how much weight, y, can a similar beam support if it's 4.8 inches wide. And now I take that k value that I found and I substitute it in. And then our new x value if the beam is 4.8 inches wide. And when I multiply 462.96 times 4.8, I'm going to get about 2,222.208. And I'll round that again. They wanted here in the directions the nearest integer. So the nearest integer is going to be 2,222 pounds. So about 2,222 pounds. And you would just put 2,222 in the box. Okay, you don't have to put this squiggly about symbol. You just put that number. So as that is all for section 7, chapter 7. So if you do have questions, please send me an email, send me a note, and I'll be sure to get back to you before you take your test. So otherwise, enjoy the rest of your day or whatever you're doing today. And we'll see you next time for reviewing for the final exam. So